Hey everybody, this is a video responding to a viewer question, only this is a very special viewer. This happens to be my son, who's in 7th grade at this moment, and they're doing a section on basic statistics, measures of central tendency, and one of the things that they've been asked to do is to compute what's called the mean absolute deviation of a data set. So if you haven't seen this before, the idea is you have a data set like you see here on the screen. You compute the mean, and then to compute the mean average deviation, what you're supposed to do is essentially compute the average distance of every point in your data set to the mean. So how do you compute the distance from a data point to the mean? Well, I might say, oh, for example, this 2. I say, how far is 2 away from the mean, 5.25? Now, if I just computed it as written, I would end up with a negative number, which isn't a very good distance. So in order to get the distance between two numbers, you're going to compute the absolute value of their difference. All right. So in this case, this would end up being 3.25. And then I would do this again. So I would do 3 minus 5.25, because that's the next data in this set. Let's see, that would be 2.25. And now I notice actually there's 4 copies of that. So let's see, there's going to be 4 of these, so that's 4 of those. Let's see, 4 by 2 is 8, and then another one is 9. Okay, and then there's 4 4s, so I'll have 4 copies of 4 minus 5.25, which the distance between 4 and 5.25 is 1.25. 4 by 1 is 4, plus another 1 is 5. Let's see, then we have 5 minus 5.25. Absolute value, that's going to be 0.25. And we keep going. 6 minus 5.25, okay, that's now going to be 0.75. And actually, we're in this position now, you see, where the data points are larger than the mean. So the absolute values we don't really need anymore. We'll write them for consistency, but they're essentially irrelevant. So it'll be 1.75, and then we're going to have 2 copies of 8 minus 5.25. All right, so that's going to be 2.75. Okay, then we got to multiply by 2, so that's 4, and another 1.5. So that's going to be 5.5. Okay, then we have the 9, so 9 minus 5.25, and that's going to be 3.75. And then finally the 11. So we have 11 minus 5.25, and that's going to be 5.75. Okay, now, in order to compute the mean absolute deviation, we want to sum all of these deviations and divide by the total number. By the way, right, we count up quickly, there are 16 points in this data set. That's what we'll be dividing by. Okay, so let's see, we add these all up. Let's see, that's okay, so this is 35 when we sum these. All right, so the sum is equal to 35. And so the mean absolute deviation is the sum divided by the total number of data points. Okay, 35 over 16, this is about 2.19. That's 2.1875, but we'll just say about 2.19. Okay, so that's how we can compute using the traditional method, the mean absolute deviation. And there's a lot of steps involved, right? Now, assuming we've already computed the mean from the beginning, and we know how many data points there are, what do we have to do? Well, in this, actually, this is kind of a nicer situation because we have some duplicate points. But you can imagine in the worst case scenario, all of the points in the data set are different. In which case, we would have been computing 16 different differences, and then having to do 16 different sums. All right, and then at the end we would do this division. So now, okay, actually, I'm being a little bit careless with my math, right? So yes, you do have to do these 16 different differences. When you sum, there's 16 points, you only have to do 15 sums. Okay, so, but at the end of the day, you also have to do this one division. So in total, we would have done 16 differences, 15 sums, and one division. So that'd be 2 times 16 operations. All right, so 2 times 16, right? Because it's 116 plus 16 minus 1, but plus 1. So 2 copies of 16, 32 operations in order to compute this. Now, once you're a grown up, of course, you're never doing this by hand, right? But when you're in school, they're going to have you do some of these things by hand. And 32 is a lot of different operations to do. There's a lot of chances you can make a little arithmetic error, even if it is you know what you're doing. Now, of course, the reason why I expect they're having people do this by hand is in order to internalize this formula, right? Compute these absolute differences and then take the average. They want them to get that. Now, assuming that somebody actually has internalized the idea of what the mean absolute deviation is doing, I wanted to know, for the sake of my son, was there a faster way of doing these computations that, well, of course, obviously here doing the 4 times, that certainly simplified matters for us, right? We didn't have to do 32 operations, right? We were able to cut it down a little bit. But could we cut it down in general? Could we simplify this? All right, so next I'm going to show you here a mad hack. So the way this hack's going to work is, let me copy the data set down. So the first step is I'm going to chop the data at the mean. Okay, so just like before, we're assuming we've already worked out the mean, and I'm just going to chop it at the mean. So I'll just put here a little 5.25 so we remember what that is. Okay, and the important thing is how many data points are below and how many data points are above. And that's an easy thing to actually compute. I just count them up really quickly. It looks like 10 on this side and 6 on this side. That's not, I hardly even consider that a computation. Okay, next, I'm going to subtract this number on the right from the number on the left. So here I get 10 minus 6 is equal to 4. So 10 minus 6 is equal to 4. No problem, right? Okay, I want to multiply this difference by the mean. So I'm going to compute the mean, 5.25, times this number 4. Okay, so this is kind of the one place we're actually going to have to deal with the mean, right? Which is nice, because here we had to constantly be subtracting this 5.25, which is gross. Like maybe they're nice and they give you a mean, which is an integer value, but when it's got a decimal, man, that's not so fun. So here we just have to one-time compute this product. So let's see, 20 and 1 is 21. Okay, no problem there. Now, I'm going to go back to the data set, and I don't have to think about the mean anymore. This is the really cool part of this hack. And what I'm going to do is I'm going to start on the right side, and I'm going to just keep on adding up the numbers until I get to my line split, right? My data split. After which I'm going to start subtracting. So I'm going to go 11 plus 9 is 20, 28, 36, 43, 49, and maybe I'll write this here just in case I think I've made a mistake or something, and I want to go back and start at some reasonable point again, right? It's good to do that. And now this minus here that we wrote to do 10 minus 6 is also a reminder I should be starting to subtract these numbers. So 49 minus 5, 44, 40, 36, 32, 28, 25, 22, 19, 16, 14. So I'm going to compute this number and I get 14. So this is going to be, I'm just going to call this the plus minus number is equal to 14. And now here's the cool bit. I'm going to compute the MAD by simply summing these two numbers, 21 and 14, and again dividing by the total number of data points. So I get 35 over 16, which we already saw was going to give us the correct answer. This is about 2.19. Okay. This can be done in your head much, much faster than the usual one. And how many operations did we have to do in this case? So let's see. If we count this original step where we count the data points to the left and to the right. We'll count those as two computations. Um, so let's see. We had to do those two counts. We had to do this difference, so that's 3. Multiplying by the mean, so that's 4. And then we had to do the sum and differences. So there's 16 data points, so that's 15 operations. So we're up to 19. And then we had to add 21 and 14, that's 20. And then we had to divide by 16, so that was 21. So we ended up doing 21 operations. Okay, of course, we could have done some things a little simpler in our mind. We had, for example, noticed we had 4 4s. We might have just subtracted 16 instead of doing them one at a time and so forth. Okay, but being naive about everything, and maybe these weren't duplicated data points, right? We ended up having to do 21 operations versus 32 operations. Okay. And in general, what would it have been? Well, we would have still done the 2 counts, right? We do a subtraction, that's 3. We multiply by the mean, that's 4. Then, if we have n data points, we have to do n minus 1 of these subtractions or additions. So n minus 1 plus the 4 is n plus 3. Add these together, that's n plus 4. Divide one time, that's n plus 5. So in the original version, so more generally, we have to do 2 times the number of data points operations. But using this mad hack, so generally, we only have to do n plus 5 operations. And so as n grows, you can see 2n versus n plus 5, right? N plus 5 is going to be about half as many steps as n gets very, very large, right? Now, obviously, in the context of, say, middle school, they're not going to let n get very large. You're going to have 1,000 data points that you're doing here. But even in this case, we see we only had to do about 2/3 the number of operations. So that's pretty good. Okay, so why? Right? Like, why does this work? Okay, and this is, of course, the cool conceptual question. So let's go back to the original formula. In the original formula, we're taking a sum of all of these differences. So I might have a data point x sub I minus the mean. All right, so we're going to write this as x bar. Okay, so this is the data point minus the mean. We're going to sum this over all the i's. So I here will go from 1 to our n, right, capital N. And then at the end, we divide by the number of data points. So this is how we compute the MAD in general. Okay, now we saw when we were computing the MAD using the traditional method that at some point, namely wherever we went from below the mean to above the mean, we didn't really need the absolute values anymore. So what I'm going to do is take this formula and break it up. Okay, so we're going to have 1 divided by n, but now I'm going to do a sum, and I'm not going to index it in the same way. I'm just, because we're breaking things up sort of in some arbitrary spot. Well, it's not arbitrary to us, but from the notation it looks arbitrary. So when the xi's are less than the x bar, so here we're going to do it where the xi's are less than the x bar, then this is going to give me xi minus x bar absolute value, which is, well, because I know this is xi is less than x bar, that actually should be negative, and then the absolute value wants to make it positive. And so it needs to put a negative sign in front. So the absolute value will just become the negative of xi minus x bar, or if you prefer, this is just x bar minus xi. Okay, now, once you get to the point where it's greater than the mean, or even just equal, say, we don't need the absolute values anymore. So here, where the xi is at least as big as the mean, then I can just drop the absolute values. I could choose parentheses if I like. Okay, so then what happens? Well, I can actually break this sum up because you notice this x bar is the same every single time. So I can rewrite this now as a sum of all of the, well, let's see, first, there's the x bar, right? We'll use the green version. If I take the x bar, I'm just basically saying count, so number of xi less than x bar. So I take that number times x bar. Okay, and then we're going to have minus the sum of all of the xi's when the xi is less than x bar. Okay, so this is what happens to the first summation. Okay, now the second summation, I'm summing over all xi's that are at least as big as x bar, all the xi's, and I'm going to subtract now the number of xi greater than or equal to x bar times x bar. Okay, and now let me rearrange to take the first bit and the last bit and put them together. So this is equal to 1 over n times. So I take the number of xi's less than x bar, and I'm going to subtract from that the number of xi's greater than or equal to x bar. So this is the number of xi's less than x bar minus the number of xi's greater than or equal to x bar times the mean. And now let's jump back up and look. The first thing we did was we counted how many were less than the mean, how many were greater than the mean, and we subtracted the ones that were greater from the ones that were less. And that's exactly what we're doing here at this step. The number of xi's less than x bar, subtracting the number of xi's greater than x bar, and then we multiplied that by the mean. Okay, now what's left over? Well, let's write this in the different order. First, I'm going to add all of the xi's that are at least as big as x bar. So I sum all the xi's that are at least as big as x bar. And then I'm going to subtract all of the xi's that are less than x bar. And that's exactly what we were doing in this next step. This is how we got the 14. We started from 11. We added all the ones that were greater, and then we subtracted all the ones that were less. And then we add them together, if you like. Add this to this number that we got by multiplying this difference by the mean, and then we divide by the number of data points. Okay, so this is an algebraic verification that this mad hack actually works. Okay, so this is, I think, a good advertisement for what can happen if you decide to use a little bit of algebra, right? Somebody gives you a formula and you notice perhaps that the same thing gets used every single time. Like here, the x bar. The xi is changing, but the x bar is the same. And so by just using a little bit of cleverness with the absolute value and a little bit of algebra, we're able to come up with an algorithm that uses substantially fewer operations and would make this easier to do by hand. Now, obviously, in doing so, you are losing all of the conceptual nature of this process, right? Computing the averages of those differences. But if you already have that under your belt, then, man, this seems like a much nicer way of doing this if you're forced to do it by hand. All right, everybody. This was really fun. We will see you next time.